This is the electromagnetic induction section of spiral physics. Despite the fact that induction is pronounced induction, it has nothing to do with ducks, but I still like it. And in one of our lectures, we're going to have an appearance by a duck, so you can look forward to that. So back in the electric field section, we studied Gauss's law, and now we're going to study Faraday's law, named after Michael Faraday, who is an English physicist. What I'm going to show you now is from the Introduction to Electrodynamics book by David Griffiths. So you might be interested in reading more about that there. So in the Griffiths book, he talks about 3 different experiments that Michael Faraday did, and he said you can characterize the experiments as follows with some violence to history. So this is the first experiment that we have. We have a magnetic field in this region that I've shaded in blue, and I'm going to say the magnetic field is coming out of the page. And if you take a current loop with a resistor in it here and pull the current loop to the right so that it has a velocity going to the right, you now have charged particles moving in a magnetic field, because in the wire, even if the net charge for the wire is 0, you still have charged particles in the wire which are free to move. And these charged particles are electrons, but the direction that the electrons flow in is the opposite of the direction that the current is flowing in, so it would be easier to pretend that they are positively charged particles, and then we will still get the current flowing in the same direction when we use our right-hand rule for the equation that we had in the previous section, which is force is equal to QV crossed with B. So on this side of the wire, you have charged particles. They're moving this way. I'm going to turn the paper to make it easier. So we have the velocity pointing this way, magnetic field pointing out of the page. So if they were positively charged particles, you would have a force acting downward on this side of the wire. You also have a force acting downward, let me turn my paper again, on this side of the wire, on this side of the wire also, but the problem is the particles on the top and the bottom of the wire can't actually move downward. Well, they can't move downward very far if it's a thin wire. But over here, the particles can move downward, and this will cause a current to flow in this direction in the wire. So we have charged particles moving in a magnetic field. Because the particles are moving in a magnetic field, we have a force exerted on the particles. Because they are free to move downwards, we will have current flowing in the wire. So that is the first experiment. In the second experiment, we have the same relative motion, but now we're going to move the magnetic field instead of moving the loop of wire. So we're going to still have the magnetic field pointing out of the page. If you take Physics 262 next semester, you will see that the relative motion is the only thing that matters. So it really shouldn't matter. Whoops, the loop is not supposed to move there. The loop is supposed to be still, and you move the wire. So it's only the relative motion that matters, so you should still get a current induced in the same direction because the relative motion is the same. However, the equation that we had here was only good for when the velocity of the particles was not 0. If the velocity of the particles is 0, then this equation says that the magnetic force acting on the particles is equal to 0. But something is causing the charges to move in the wire, and this equation says it can't be the magnetic force because the particles are actually at rest. Therefore, we must conclude that there is another force acting on the charged particles. It's not a magnetic force. The other force that we can have acting on charged particles, I mean, you could have the force of gravity, but it's very small. So you could have an electric force acting on charged particles, and the electric force still acts on those charged particles even when they are stationary. This caused Michael Faraday to conclude that changing magnetic fields create or induce electric fields. So in this experiment here, we have an induced electric field, which is then going to cause the current to flow. That's all we really need to know for now, but later on in this section, we will look at exactly how we can figure out what that electric field is. And if changing magnetic fields induce electric fields, there's two ways that you can change the magnetic field. You can take the magnetic field and you can move it. So you could pretend that this is the magnetic field that you have between two poles of a magnet. You could move, kind of like what we had in the force on a conductor lab. You could move the magnet, or this doesn't really work with a magnet, but it would work if your magnetic field was created by current flowing. If you change the current, that changes the strength of the magnetic field. So you could also change the strength of the magnetic field, and that would be a changing magnetic field. So you should have an electric field induced in this case also, which should again cause the current to flow. Oops. And depending on whether you increase the current or decrease the current, increase the field or decrease the field, the current would flow in different directions. But let's just say we change it such that the current flows this way. And we'll learn later whether you'd have to increase it or decrease it to get the current to flow this way. Okay, so those are 3 experiments, and from this, Michael Faraday concluded that changing magnetic fields induce electric fields. Okay, now for the first problems that we're going to be looking at in this section, we're not going to worry about Faraday's law, but we're going to just look at the signs that you would have from Faraday's law, and that's just actually called Lenz's law, and you can state Lenz's law as follows. This is, again, from the Introduction to Dynamics, where David Griffith says, Lenz's law states that nature abhors a change in flux. Okay, so that actually comes from Faraday's law when you look at the signs, but if you just want to know the direction, that comes from Lenz's law, which states that nature abhors a change in flux. And that is how Griffiths states Lenz's law. And we'll see exactly what we mean by nature abhorring a change in flux in our next problems.